Welcome to our lecture on the refraction of light. Today, we're going to explore what happens when light travels from one medium to another and why it doesn't always travel in a perfectly straight line. Let's start with the basics. Refraction is simply the change of direction of light as it travels from one medium into another. But why does it bend? The bending is actually a result of a change in speed. When light moves from air into water or glass, it slows down. Because the speed of light in air is higher than in glass or water, we say that glass and water are optically denser than air. This change in speed causes the light ray to pivot or bend unless it hits the boundary perfectly straight on. To understand the laws governing this bending, we need to define some geometry. Imagine a ray of light, which we'll call the incident ray, OA, hitting the boundary between two media at point O. We draw an imaginary line perpendicular to the surface at this point, called the normal. The angle between the incident ray and the normal is the angle of incidence, denoted as I. As the light enters the second medium, it bends, becoming the refracted ray, OB. The new angle it makes with the normal is the angle of refraction. Now we can establish the two fundamental laws of refraction. The first law states that the incident ray, the refracted ray, and the normal all lie in the exact same flat plane. You won't have a ray coming in flat and then bending up off the page. The second law, famously known as Snell's law, is mathematical. It states that for any given pair of materials, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. We call this constant the refractive index, represented by the letter n. Let's put Snell's law into practice with an example. Suppose a ray of light travels from air into glass with an angle of incidence of 60 degrees. We are given that the refractive index of this glass is 1.52. We want to find the angle of refraction, r. We set up our equation. 1.52 equals the sine of 60 degrees divided by the sine of r. The sine of 60 is approximately 0.866. Rearranging to solve for sine of r, we divide 0.866 by 1.52, giving us 0.569. Taking the inverse sine, we find that the angle of refraction is 34.7 degrees. Here is a second example. This time, light hits water, which has a refractive index of 1.33, at an angle of incidence of 45 degrees. Using Snell's law, 1.33 equals the sine of 45 degrees divided by the sine of r. The sine of 45 is 0.707. Dividing 0.707 by 1.33 gives us 0.531. Taking the inverse sine of 0.531 reveals an angle of refraction of 32.1 degrees. Notice how the light bends closer to the normal because it's entering a denser medium. To solidify this, here are 3 exercises you can try on your own. The first asks you to find the refractive index given both angles. The second is a straightforward application of Snell's law to find the refraction angle. The third introduces a slightly more complex scenario, a boundary between water and glass rather than air and a medium. You'll need to use the relative refractive index between the two materials to solve this one. We defined refractive index using angles, but it has a deeper physical meaning. The absolute refractive index of a material is actually the ratio of the speed of light in a vacuum to the speed of light in that specific medium. The speed of light in a vacuum, denoted by c, is a universal constant, 3 × 10⁸ meters per second. Because light travels fastest in a vacuum, the refractive index n is exactly 1 for a vacuum, and greater than 1 for any other medium, like 1.33 for water or 1.5 for glass. An elegant property of optics is the principle of reversibility of light. It simply states that the paths of light rays are perfectly reversible. If a light ray travels from medium 1 into medium 2 and bends along a specific path, a ray originating from medium 2 and sent back along that exact refracted path will emerge into medium 1 along the original incident path. The geometry works identically in both directions. Building on Snell's law, what happens if light passes through multiple parallel layers? Imagine light moving from air through medium 1, then medium 2, and back into air. If we apply Snell's law at the first interface, we find that the sine of the angle in air equals the refractive index of medium 1 times the sine of its angle. Applying this logic across all boundaries reveals a powerful universal rule. The product of the refractive index of a medium and the sine of the angle in that medium is always constant across parallel boundaries. To summarize the behavior of light at boundaries, we have a few handy rules. When a ray travels from a less dense medium to a denser medium, like from air to glass, it slows down and is refracted towards the normal line. Conversely, when traveling from a denser to a less dense medium, like glass back out to air, it speeds up and bends away from the normal. And importantly, if light hits the boundary dead-on at 90 degrees, it changes speed, but its direction doesn't change at all. It passes straight through. We will use these rules to solve more complex multilayer problems next. Moving right along, let's dive into the fascinating phenomenon of total internal reflection. When a light ray travels from a more optically dense medium, like glass, into a less dense medium, like air, it bends away from the normal. At this boundary, some of the light is weakly reflected back, but the majority of it is refracted outward. As we gradually increase the angle of incidence, the angle of refraction also increases. Eventually, we hit a specific tipping point. At a certain angle of incidence, the refracted ray bends so much that it grazes the exact boundary between the two media, making the angle of refraction exactly 90 degrees. We call this specific angle of incidence the critical angle, denoted by the letter C. Now, what happens if we increase the angle of incidence even further, pushing it beyond that critical angle? The light can no longer refract into the less dense medium at all. Instead, the entire ray is totally reflected back into the denser medium. This complete bounce back is what we call total internal reflection. For total internal reflection to occur, two strict conditions must be met simultaneously. First, the light must be trying to travel from a more optically dense medium into a less dense one, for example, moving from glass into water or water into air. Second, the angle at which the light hits the boundary must be strictly greater than the critical angle for that specific material pairing. We can mathematically link the critical angle to the refractive index using Snell's law. If light moves from a dense medium with refractive index n into air, which has an index of 1, we set the angle of incidence to c and the angle of refraction to 90 degrees. Since the sine of 90 degrees is exactly 1, the equation simplifies beautifully. The sine of the critical angle equals 1 divided by the refractive index. Let's apply this formula. If we have glass with a refractive index of 1.5, we take the inverse sine of 1 over 1.5, which gives us a critical angle of 41.8 degrees. For water, which is less dense than glass and has a refractive index of 1.33, the critical angle is slightly different. The inverse sine of 1 over 1.33 gives us 40.75 degrees. Consider a classic experiment using a semicircular glass block. A light ray passes through the curved side, hits the flat face, and forms a bright spot on a nearby screen. If we slowly rotate the block, the spot moves down the screen and suddenly disappears at a specific distance. Why? Because as we rotate the block, the angle of incidence increases until it just exceeds the critical angle, causing total internal reflection. The light is trapped inside, so the spot vanishes. We can actually use the geometry of that disappearing spot to find the glass's refractive index. By taking the inverse tangent of the distances, 1.68 centimeters down over 1.5 centimeters across, we find the angle of the emerging ray is 48.2 degrees. Using the geometry of the triangle formed, we deduce the critical angle inside the glass is 41.8 degrees. Plugging this into our critical angle formula, we calculate the refractive index of the block to be 1.5. Total internal reflection creates some amazing natural optical illusions, like mirages. On a hot day, the air near the ground is hotter and less dense than the cooler air above it. As light from the sky travels downward, it continuously refracts away from the normal as it hits these less dense layers. Eventually, it hits the critical angle and totally internally reflects upward. Our brains assume light travels in straight lines, so we interpret this skylight as a shimmering pool of water on the ground. In modern technology, we harness this principle in optical fibers. These are transparent cables coated with a cladding material of lower optical density. Light enters the core and strikes the boundary at an angle greater than the critical angle. It bounces repeatedly down the pipe without escaping. This is how doctors look inside the human body using endoscopes, and how global telecommunications transmit TV and internet signals using laser light. This concept even applies to radio waves. A transmitting station sends radio waves skyward into the ionosphere, specifically a region called the Appleton layer. As the wave enters this less dense atmospheric layer, it continuously refracts away from the normal until it undergoes total internal reflection. It then bounces back down to Earth, allowing a receiver far over the horizon to pick up the signal. Prism binoculars use totally reflecting isosceles right-angled prisms to fold the path of light. Prism A laterally inverts the image from the objective lens, and Prism B inverts it vertically. This ensures the final image you see is the right way up and the right way round. Because the light path folds back on itself through 180-degree reflections, the effective focal length is tripled without making the binoculars physically long and bulky. Why use prisms instead of plain mirrors in these optical devices? First, mirrors require a silver coating that degrades and wears off over time, whereas solid glass prisms do not. Second, prisms reflect light via total internal reflection, with zero loss of energy, unlike mirrors which absorb a small fraction of the light. Finally, the thick glass of plain mirrors can create annoying multiple faint reflections, but prisms provide one crisp, clear image. Let's look at a clever laboratory technique, the air cell method for finding the refractive index of a liquid. We place a parallel-sided air cell, which is just a thin layer of air trapped between two glass plates, inside a vessel filled with the test liquid. We shine a monochromatic light through the whole setup and look from the opposite side. We start with the air cell perfectly perpendicular to the light beam. Then we slowly rotate it. At a specific angle, the light is suddenly cut off from our view because it hits the critical angle at the glass air boundary inside the cell. We note this angle of rotation. To be precise, we return to the start and rotate it the opposite way to find the cutoff point again, then average these two angles to get our final measurement, theta. The math behind this is quite elegant. When the light is cut off, it's grazing the glass air boundary inside the cell. By applying Snell's law across the liquid, glass, and air layers, the intermediate glass terms actually cancel out. We find that the refractive index of the liquid is simply 1 divided by the sine of alpha. Since our measured angle theta is twice alpha, the liquid's refractive index is 1 over the sine of theta divided by 2. Shifting our focus to prisms. A prism is a geometrical glass object with flat refracting surfaces. The angle between the two inclined surfaces is called the refracting angle, A. When a light ray enters, it moves from less dense air to denser glass, bending towards the normal. Upon exiting, it moves back into the air, bending away from the normal. Because of the prism's geometry, the net result is that the ray always deviates towards the base of the prism. Because the prism bends the light, the emergent ray travels in a different direction than the original incident ray. The angle between these two directions is called the angle of deviation, D. By looking at the geometry of the normals and the refracting angle A, we can prove that the total deviation equals the sum of the incident and emergent angles minus the refracting angle A. There is a special case called minimum deviation. If you continuously change the angle of incidence, the deviation angle changes, forming a U-shaped curve on a graph. It reaches its absolute minimum value when the light ray passes perfectly symmetrically through the prism. At this minimum point, the angle of incidence exactly equals the angle of emergence, and the internal ray travels parallel to the base. This symmetrical case gives us a powerful way to measure the refractive index of the glass. Since the angles are equal, our deviation formula simplifies. We can express the incident angle as the minimum deviation plus A, all divided by 2. Plugging this into Snell's law gives us a standard formula. The refractive index equals the sine of the incident angle over the sine of the refracted angle, expressed entirely in terms of measurable prism angles. What if the prism is very thin, with a refracting angle of 10 degrees or less? For these small angle prisms, we can use the small angle approximation, where the sine of an angle is roughly equal to the angle itself in radians. When we substitute this into Snell's law at both faces, the complex sine formula simplifies dramatically. The deviation produced is simply the refractive index minus 1 multiplied by the refracting angle A. Another interesting extreme is the grazing property. If a ray emerges from the prism exactly along the glass air boundary, we say it grazes the surface. This means the angle of emergence is exactly 90 degrees, which implies the light hit the second internal face at exactly the critical angle. By substituting the critical angle into our prism equations, we can derive a specific formula to calculate the refractive index based solely on the incident angle and the refracting angle. Now for the beautiful part, dispersion. White light is actually a mixture of many colors. When it enters a transparent medium like a prism, each component color travels at a slightly different speed. Because of this, each color experiences a slightly different refractive index and bends by a different amount. Violet slows down the most and bends the most, while red bends the least, fanning the white light out into a brilliant rainbow spectrum. We can measure this color spread using a concept called angular separation. If we look at just two colors, say blue and red, passing through a small angle prism, we can calculate the difference in their deviation angles. The angular separation, denoted by phi, is simply the difference between their specific refractive indices multiplied by the prism's refracting angle A. To measure these prism angles and deviations precisely in a laboratory, we use an optical instrument called a spectrometer. It consists of three main components: a collimator to produce a perfectly parallel beam of light, a rotatable turntable equipped with leveling screws to hold our prism, and a movable telescope with crosshairs for the observer to precisely track the refracted light. Before taking any measurements, we must carefully calibrate the spectrometer. First, we focus the telescope on a distant object so it is set to receive parallel light. Then, we look directly at the collimator through the telescope and adjust the collimator's length until its slit is perfectly sharp, ensuring it emits parallel rays. Finally, we use the screws on the turntable to ensure the prism will sit perfectly level. Let's transition from flat prisms to curved lenses. A lens is a piece of glass bounded by spherical surfaces. You can think of it as a stack of tiny prisms. A converging or convex lens is thicker in the middle and bends parallel light rays inward to converge at a single focal point. A diverging or concave lens is thinner in the middle and spreads light rays outward, making them appear to diverge from a focal point behind them. To draw accurate ray diagrams, we need to define some terminology. The principal axis is the imaginary line passing straight through the centers of curvature of the lens. The optical center, C, is the exact middle of the lens. Light passing through here does not deviate. The principal focus, F, is where parallel rays converge, and the distance from the optical center to this focus is called the focal length. When determining where an image will form, we rely on three principal rays. First, any ray traveling parallel to the principal axis will refract through the principal focus. Second, any ray passing through the principal focus first will refract to become parallel to the axis. And third, any ray passing straight through the optical center will continue in a straight line without bending at all. Let's look at a specific case of image formation. If we place an object very close to a convex lens, between the focus and the optical center, the refracted rays diverge. If we trace them backward, they intersect to form an image that is virtual, upright, and magnified. This specific setup is exactly how a standard magnifying glass works. If we move the object further back, placing it between F and 2F, the behavior changes. The rays now physically converge on the other side of the lens. This forms a real image that can be projected onto a screen. The resulting image is inverted, magnified, and located beyond the 2F mark. This is the optical principle used in film and slide projectors. For a diverging or concave lens, the story is much simpler. No matter where you place the object along the axis, the rays will always diverge outward. By tracing them back, they will always intersect to form an image that is virtual, upright, and diminished, meaning smaller than the object. These lenses are commonly used in spectacles to correct short-sightedness. We can calculate exactly where an image will form using the thin lens formula. 1 over the focal length equals 1 over the object distance, u, plus 1 over the image distance, v. We must use a strict sign convention here. Real objects and real images have positive distances, while virtual images have negative distances. Furthermore, convex lenses always have a positive focal length, while concave lenses have a negative one. Optometrists and physicists often talk about the power of a lens rather than its focal length. The power is simply the reciprocal of the focal length, provided the focal length is measured in meters. The standard unit is the diopter. So a converging lens with a 15 centimeter focal length has a power of 1 divided by 0.15 meters, giving a positive power of 6.67 diopters. If we place two thin lenses in direct physical contact, finding their combined power is incredibly easy. You just add their individual powers together. For instance, if we combine a 10 diopter convex lens with a -4 diopter concave lens, the total power of the combination is simply 10 minus 4, giving us a net power of 6 diopters. This mathematical simplicity leads us perfectly into our next topic on magnification. Continuing our discussion on lenses, let's look at linear or lateral magnification. Magnification is defined as the ratio of the height of the image to the height of the object. Equivalently, it can be defined as the ratio of the distance of the image from the lens, v, to the distance of the object from the lens, u. To see why magnification equals v over u, consider the formation of a real image by a convex lens. A ray passing through the optical center is undeviated. This creates two similar triangles, one between the object and the optical center, and one between the image and the optical center. The ratio of their heights, which is the magnification, is exactly equal to the ratio of their distances from the lens, v over u. Let's apply this to an example. If an object is placed 20 centimeters from a converging lens with a focal length of 15 centimeters, we can find the image position using the thin lens formula. Solving for V gives us positive 60 centimeters, meaning it is a real image. The magnification is V over U, which is 60 over 20, giving us 3. So the image is real and 3 times larger than the object. In another scenario, suppose we have a virtual image that is 4 times magnified, with the object at 12 centimeters. Since magnification is 4, the image distance V is 4 times 12, or 48 centimeters. Because it is a virtual image, we use negative 48 centimeters in the lens formula. Solving for the focal length F gives us 16 centimeters. What is the minimum distance between an object and its real image formed by a convex lens? If we let the total distance be d and the image distance be x, the object distance is d minus x. Substituting these into the lens formula yields a quadratic equation for x. For x to be real, the discriminant must be greater than or equal to 0. This reveals that the distance d must be at least 4 times the focal length. This brings us to the concept of conjugate points. These are pairs of points on the principal axis where, if you place an object at one point, the image forms at the other, and vice versa. If we measure the object and image distances from the focal points rather than the lens, calling them x and y, we can derive Newton's equation. The focal length squared equals x times y. If we keep an object and a screen fixed at a distance L apart, there are often 2 lens positions that will focus a clear image on the screen. Let's say the lens is displaced by a distance d between these 2 positions. Using the property of conjugate points, we can express the object and image distances in terms of L and d. Plugging these into the lens formula gives a very useful equation. The focal length equals L squared minus d squared, all divided by 4L. This displacement method also gives us a clever way to measure the height of an inaccessible object. At the first lens position, the magnification is the image height h1 over the object height h. At the second position, the object and image distances are swapped, so the magnification is h2 over h. Multiplying these relationships shows that the true object height is the geometric mean of the 2 image heights, the square root of h1 times h2. To summarize the requirements for a convex lens to form a real image on a screen, first, the object must be placed further from the lens than its focal length. Second, as we proved earlier, the total distance between the object and the screen must be at least 4 times the focal length of the lens. Let's look at a quick example. A converging lens with a 15 centimeter focal length forms a real image twice the size of the object. We can use the rearranged magnification formula. M equals V over F minus 1. Plugging in a magnification of 2 and a focal length of 15, we find the image distance is 45 centimeters. What if a convex lens of focal length 15 centimeters forms an image 3 times the object's height, but we don't know if it is real or virtual? We must consider both cases. If the image is real, V equals positive 3u, which gives an object distance of 20 centimeters. If the image is virtual, V equals negative 3u, resulting in an object distance of 10 centimeters. Now let's analyze systems with multiple lenses. Here, 2 convex lenses are 20 centimeters apart. An object is placed 6 centimeters from the first lens. Using the lens formula, the first lens forms an image 30 centimeters away. Since this is 10 centimeters past the second lens, it acts as a virtual object for the second lens, so U is negative 10. The final real image forms 6 centimeters from the second lens, with a total system magnification of 3. If we replace the second lens with the diverging lens, the process is similar. The first lens forms an image 60 centimeters away, which is 10 centimeters past the diverging lens. This virtual object distance of negative 10, combined with the diverging lens's negative focal length, results in a final real image 30 centimeters from the diverging lens. The total magnification is the product of the individual magnifications, giving us 15. When light from a distant object enters a converging lens, the image forms exactly at its focal point, in this case 20 centimeters away. If a diverging lens is placed 12 centimeters after the first lens, the intermediate image is 8 centimeters past it, acting as a virtual object. The diverging lens then forms a final virtual image 24 centimeters behind itself. Let's apply the displacement method to an example. An object and screen are fixed, and a lens forms an image with a magnification of 2.5. The lens is then moved 30 centimeters to form a second sharp image. Because the magnification is V over U and the displacement d is V minus U, we can solve for U and V, finding them to be 20 and 50 centimeters. The total distance L is 70. Using either the thin lens formula or the displacement formula, the focal length is 14.3 centimeters. Moving on to practical applications, how do we measure the focal length of a convex lens? The simplest method is to focus a distant object onto a screen. The image distance is approximately the focal length. A more precise laboratory method uses a plane mirror behind the lens. By adjusting a pin above the lens until it perfectly aligns with its own reflection without any parallax shift, the distance from the pin to the lens is exactly the focal length. Another variation uses an illuminated object, like crosswires, and a plane mirror. You adjust the lens until a sharp image forms right next to the object on the screen. That distance is the focal length. Alternatively, you can use the standard thin lens formula. By measuring multiple pairs of object distance u and image distance v, you can plot the product u times v against the sum u plus v. The slope of this graph gives the focal length. We can also use the displacement method we derived earlier. By keeping the object and screen fixed at a distance L and finding the two lens positions that yield a sharp image, we measure the displacement d. We then calculate the focal length using L squared minus d squared over 4L. This method is especially useful for thick lenses or lenses fixed inside a tube, where measuring from the optical center is impossible. Diverging lenses are trickier because they don't form real images on their own. To measure their focal length, we first use a converging lens to form a real image. We then place the diverging lens in the path of the converging rays. The original image acts as a virtual object for the diverging lens, which forms a new real image further away. By measuring these distances, we can calculate the diverging lens's focal length. Another method pairs the diverging lens with a concave mirror of known focal length. We adjust the object until it coincides with its final image. For this to happen, the light rays must strike the mirror at a normal angle, meaning they appear to come from the mirror's center of curvature. Therefore, the virtual image formed by the diverging lens is located exactly at the mirror's center of curvature. Let's see this in practice. An object is 20 centimeters in front of a diverging lens, and a concave mirror with a 15 centimeter focal length is 20 centimeters behind the lens. The mirror's center of curvature is at 30 centimeters. Since the mirror is 20 centimeters from the lens, the virtual image is 10 centimeters behind the lens, so v is negative 10. Using the lens formula with u as 20 gives a focal length of negative 20 centimeters for the diverging lens. When two thin lenses are placed in direct contact, their combined effect is equivalent to a single lens. The image formed by the first lens acts as the object for the second. By adding the thin lens equations for both lenses, the intermediate image distance cancels out. The result is that the reciprocal of the combined focal length equals the sum of the reciprocals of the individual focal lengths. For example, if we combine a converging lens with an 8 centimeter focal length and a diverging lens with a negative 12 centimeter focal length, we simply add their reciprocals. 1/8 minus 1/12 equals 1/24. The combined focal length is positive 24 centimeters, meaning the pair behaves as a single, weaker converging lens.
How does the physical shape of a lens determine its focal length? By treating a thin lens as a series of small prisms, we can relate the deviation of light to the refractive index, n, and the radii of curvature of the two surfaces, r1 and r2. This derivation leads to the lensmaker's equation. 1 over the focal length equals n minus 1, multiplied by the sum of 1 over r1 and 1 over r2.
To use the lensmaker's equation correctly, we must follow a strict sign convention. If a surface is convex, bulging outward toward the incoming light, its radius of curvature is positive. If it is concave, curving inward, its radius is negative. For meniscus lenses, which have one convex and one concave surface, pay close attention to which radius is larger to assign the signs properly. Let's calculate the focal length of a converging meniscus made of glass with a refractive index of 1.5. The convex surface has a radius of 6 centimeters, so R1 is positive 6. The concave surface has a radius of 15 centimeters, so R2 is negative 15. Plugging these into the lensmaker's equation, we find the focal length in air is positive 20 centimeters. Real lenses aren't perfect. They suffer from optical defects called aberrations. The first is chromatic aberration. Because the refractive index of glass varies slightly with color, a lens bends blue light more sharply than red light. As a result, different colors focus at slightly different points along the principal axis, causing the final image to have blurred, rainbow-colored edges. To fix chromatic aberration, optical engineers use an achromatic doublet. This is a combination of a convex lens and a concave lens, made from two different types of glass, like crown and flint glass. The convex lens provides the overall focusing power, while the concave lens is carefully chosen to exactly cancel out the color dispersion, bringing all colors to a single focus. The second major defect is spherical aberration. In a lens with a wide aperture, light rays hitting the outer edges, called marginal rays, are bent more strongly than the paraaxial rays near the center. Because they don't all converge at the same point, the resulting image is blurred and out of focus, even if the light is monochromatic. How do we minimize spherical aberration? For lenses, we can use a circular stop, an opaque disc with a hole in the middle. This blocks the problematic marginal rays, allowing only the central periaxial rays to form the image, though this does reduce the image's brightness. For mirrors, the solution is to use a parabolic shape rather than a spherical one, which naturally brings all parallel rays to a perfect single focus, which leads us to our next topic. Let us examine the projector lantern. A projector is designed to throw a magnified, real image of a film or transparency onto a screen. Looking at the diagram, a strong source of light, the lamp, is placed at the center of curvature of a concave reflector. Light from this source is reflected back onto the condenser, which then concentrates the light uniformly onto the slide. Finally, the projection lens takes the light passing through the slide and forms a magnified real image on the screen. Each component of the projector has a specific and vital function. The concave reflector ensures no light is wasted by concentrating light from the back of the lamp forward onto the condenser. The condenser's job is to uniformly illuminate the slide, preventing hot spots and concentrating the light toward the object. The slide itself bears the object or film to be projected. The projection lens is responsible for focusing and magnifying the light to form an upright image on the screen, which is the surface where the final image is viewed. When calculating the magnification of a projector, we use the standard lens equations. Magnification, m, is equal to the image distance, v, divided by the object distance, u. It can also be expressed as v over f minus 1. This relationship clearly shows that to achieve a high magnification, we need a projection lens with a very short focal length compared to the distance to the screen. Additionally, when dealing with two-dimensional slides, we often use area magnification. Since the linear scale factor is the magnification m is simply the square root of the image area divided by the object area. Let's apply this to an example. A projector produces an image of 1.2 by 1.8 meters on a screen 5 meters away. The slide is 2.4 by 3.6 centimeters. We need to find the focal length. First, we calculate the areas. The image area is 2.16 square meters. The object area is 8.64 square centimeters, which we must convert to standard units, giving us 8.64 times 10 to the negative fourth square meters. Using our area magnification formula, the square root of the image area over the object area gives a magnification of 50. We then plug this into our formula. 50 equals 5 over f minus 1. Solving for f, we get a focal length of 0.098 meters, or 9.8 centimeters. For the second part of the problem, we need to calculate the distance of the slide from the lens, which is our object distance, u. We already know the magnification is 50, and the image distance, v, is 5 meters. Using the simple relation m equals v over u, we substitute our values to get 50 equals 5 over u. Solving for u gives us 0.1 meters. Therefore, the slide must be placed exactly 10 centimeters from the projection lens. Here's a slightly more complex example. We have a 7.5 centimeter square slide projected as a 4.2 meter square image. The total distance between the slide and the screen is 10 meters. First, we find the magnification using the area formula, which gives us 56. Since m equals v over u, we know v equals 56u. We are given that the total distance, u plus v, equals 10 meters. Substituting v, we get 57u equals 10, so u is 0.1754 meters and v is 9.8246 meters. Finally, using the formula m equals v over f minus 1, we plug in 56 for m and 9.8246 for v. Solving for f gives a focal length of 0.1724 meters or 17.24 centimeters. Moving on from projectors, let's look at the lens camera. A camera consists of a lens system, a light-sensitive film at the back, and a focusing arrangement used to adjust the distance of the lens for proper focusing. Light enters through the aperture, passes through the converging lens, and is refracted onto the film at the back. The film is the exact plane where the real inverted image is formed and captured. Let's break down the camera's internal mechanisms. The shutter acts as a gate, cutting off light and controlling exactly how long the film is exposed. The diaphragm regulates the amount of light entering by adjusting the size of the aperture. The focusing ring physically moves the lens to ensure the image is sharp on the film. Cameras also have to deal with optical defects. Chromatic aberration, which causes color fringing, is minimized by using an achromatic doublet, a combination of a convex and a concave lens. Spherical aberration, which causes blurriness at the edges, is minimized by using a shield with a small hole, restricting light to the center of the lens. Now let's compare the camera to its biological counterpart, the human eye. The eye is a highly specialized, light-sensitive organ for vision. Structurally, it shares many similarities with a camera, utilizing a lens system at the front to project an image onto a sensitive surface at the back. The main parts of the eye perform specific functions. The converging lens focuses the incoming light to form an image on the retina. The iris, which is the colored part of the eye, acts exactly like a camera's diaphragm. It controls the amount of light entering the eye by adjusting the size of the pupil. The pupil is simply the circular opening in the iris. Finally, the retina is the light-sensitive screen at the back of the eye, where the final image is formed, acting much like the photographic film in a camera. The parallels between the eye and the camera are quite remarkable. Both systems rely on a converging lens to focus incoming light rays. Both require a light-sensitive surface to capture the image, the retina in the eye and the film or digital sensor in a camera. Both have specific openings to admit light, the pupil and the aperture. And finally, both have dynamic mechanisms to control exactly how much light enters, the iris in the eye and the diaphragm in the camera. Despite their similarities, there are fundamental differences in how they achieve focus. The human eye has a natural, flexible lens with a variable focal length. Because the eyeball cannot change its size, the image distance, the distance from the lens to the retina, is entirely fixed. To focus on objects at different distances, the eye changes the shape of its lens. A camera, on the other hand, uses glass lenses with a fixed focal length. To focus on objects at different distances, the camera must physically move the lens, meaning the image distance is variable. This ability of the eye to alter the focal length of its lens to focus on objects at various distances is called accommodation. There are limits to this ability. The near point is the closest distance at which the eye can focus clearly, which is about 25 centimeters for a normal eye. The far point is the furthest distance for clear vision, which for a normal eye is at infinity. When the eye loses its ability to accommodate properly, either unable to make the lens thick enough or thin enough, it results in common eye defects like nearsightedness or farsightedness. To wrap up our extensive look at optical instruments, let's review the key takeaways. Microscopes utilize short focal length lenses to magnify near objects. Telescopes combine a long focal length objective with a short focal length eyepiece to view distant objects, using either lenses or mirrors. Projectors use an illumination system and a projection lens to create large, real images on a screen. Finally, cameras and human eyes operate on the same fundamental principles of focusing light onto a sensitive surface, though they solve the problem of focusing in beautifully different ways. Thank you for following along with this comprehensive study of optical instruments.